Okay, here we are given a binary search tree and our task is to find the minimum value present in the binary search tree. Our first approach will be solving this problem using Inorder traversal or the naive approach. And we know that in a binary search tree, there is this one property where the Inorder traversal of a binary search tree always gives us the values in a sorted order. So let's say we have this binary search tree, say 4, 2, 6, 1, 3, 5, and 7. And we know that Inorder traversal first gives all the nodes in a sorted order. So this is one point that is to be remembered. And Inorder traversal means we visit the left child first, then we visit the root, and then we visit the right child. So this will be the order. Let's start visiting the nodes in order traversing. We start from the left and then the root and then the right. Let's start visiting the nodes. So the order would be like 1, 2, 3, 4, 5, and 6, because we start from 1 and we go in order traversing. So basically this will be the order. Now in this naive approach, we perform an in order traversal and store all the values in an array. So let's say our sorted in order array will be like 1, 2, 3, 4, 5, 6, and 7. Since this array is already sorted, the minimum value will always be the first element. So the minimum value present in this binary search tree will be 1. This approach works, but it is not exactly optimal because we traverse the entire tree and we also use the extra space. Therefore, the time complexity will be big O of n and the space complexity also will be big O of n. Let's quickly code this approach before we move into the other approaches. Alright, let's quickly code the in-order traversal approach first. Firstly, we are defining a helper function called inorder. So def inorder, which takes in two parameters as sorted root and sorted in order. Okay, so root, which represents the current node, and sorted in order is a list where we store all the values in sorted order. So the first base case would be if root is none, we simply return. Okay, this prevents any infinite recursion and handles leaf nodes correctly. Next, according to in-order traversal, we first visit the left subtree, right? So simply we visit the left subtree as in order root dot left and sorted in order. Okay, so we make a recursive call on a root dot left, and this particular step ensures that all smaller values are processed first. And once the left subtree is completely processed, we visit the current node and add its value to the list. So simply sorted in order dot append root dot data. Because this is a binary search tree, value gets added in increasing order. And finally, we traverse the right subtree. So in order of root dot right sorted in order. So this processes all the values greater than the current node, and this completes one full in order traversal step: left, root, and right. So to summarize this function, it performs in order traversal of a binary search tree and stores all nodes values into a list in sorted order. And this sorted list will later help us to find the minimum value easily. Now that we have the in order traversal function ready, let's write the main function that uses this traversal to find the minimum value. Now let's define another function. Let's say def min value, and it takes root as the input. Okay, and now for the base case, suppose if root is none, it means the tree is empty. So in that case, we simply return -1 as there is no minimum value. And next, we gotta create an empty list called sorted in order. Sorted in order. Okay, and this list will store all the node values obtained from in order traversal. And here we call the in order traversal function. Let's say in order of root and sorted in order. So it will, what this will do is it will traverse the entire binary search tree and store all values in sorted order inside the list. And since in order traversal of binary search tree gives a sorted list, the first element of this list will always be the minimum value. So we simply return the first value of the list, that is sorted in order of 0. All right. So now let's go ahead and run the code. As you can see, for these test cases, for all the different test cases, these are the right outputs. So for this, the minimum is 1. For the next one, the minimum, the only single node, so the minimum would be 10, and so on. So this approach works by converting the binary search tree into a sorted list and then picking the first element as the answer. Okay, in the previous approach, we used extra space to store all the values, but in binary search tree, we don't actually need to do that. Let's take the same example. Let's say we have 4, 2, 6, 1, 3, 5, and 7. In a binary search tree, the left child is always smaller than the root. So if we keep moving forward, we'll eventually reach the minimum element, that is 4, 2, and 1. And here, 1 is the leftmost node, and hence that is the minimum value. So the flow is something like this. So we start from the root and we recursively call the function on the left child until the left child becomes none. That is, we start with the root min value of 4, then it goes to the next min value of 2, and finally it goes to min value of 1. And this will kind of return 1, and that answer will kind of bubble back to the root. So this logic maps directly to our recursive code. So if you want to know more in detail, it's like if root dot left, suppose if it is null, then we simply return root dot data. If that's not the case, we simply return min value of root dot left. So the recursion stops at the leftmost node, and that value bubbles up as the final answer. Here we traverse only the height of the tree and not all the nodes. So the time complexity will be big O of h, and space complexity will be big O of h as well, because we are using a recursive stack here. Now let's code this approach up. Alright, now let's write the better approach. We define the function min value, which takes the root of the binary search tree as the input. And as for our first base case, suppose if root is none, then we simply return -1. We discussed this in the earlier method as well. And for the second base case, where the left child is none, if root dot left is none, then we simply return root dot data. We discussed this as well. That is, this is like if the left child of the current node is none, it means that we have reached the leftmost node. And in a binary search tree, the leftmost node always contains the minimum value. And now next, if the left child exists, we recursively move to the left subtree. So return min value of root dot left. Okay, so this keeps pushing us towards the smaller values. So we start from the root and we keep calling the function on the left child until we find the node whose left pointer is null. So that value is returned and passed back through all the recursive calls. For example, if we have a tree, say 4, 2, 1, and the function is called on 4, then 2, and then 1. Since 1 has no left child, it is written as the answer. So now let's quickly run the code. As we can see, we got the same output as the earlier, so basically it works. Now in this condition, we are traversing the height of the tree and not all the nodes. So the time complexity is big O of h, and the space complexity is big O of h as well, because we are using a recursive call stack here. And this approach is much better than the Inorder traversal method because it avoids extra space and unnecessary traversal. However, recursion still uses stack space. In the expected approach, we'll remove recursion and solve this using an iterative method using constant space. Now let's look at the expected approach. We'll solve the same problem iteratively without using a recursion or extra space. So we have the same tree, say 4, 2, 6, 1, 3, 5, and 7. In a binary search tree, smaller values always lie on the left side. So the minimum value will always be on the leftmost node. And we'll use a pointer current to traverse at the tree. So let's say we have current here. And as long as the current node has a left child, we keep moving current to the left. And at the end, the loop stops when current.left becomes null, that is here. So since current.left is null, this means that we have reached the leftmost node. And we finally return the value stored in the current node. We only move down the height of the tree. No recursion and no extra data structure are used. So the time complexity will be big O of h, and space complexity will be big O of 1. And this is the most optimal way to find the minimum value in a binary search tree. Now let's look at the coding part now. Now let's code the iterative approach. So we define a function min value which takes the root of the binary search tree here. And let's handle the first empty tree condition, where if root is none, we simply return -1. That is, if the tree is empty, the root will be none, and in that case there is no minimum value, so we return -1. And now we got to initialize a pointer, say current is root, and this pointer will help us to traverse the tree. Now we got to use a while loop, say while current dot left is not none, then current is current dot left. Okay, That is, as long as current node has a left child, we move current to the left. In a binary search tree, smaller values always lie on the left, as we discussed. So this loop keeps pushing us towards the minimum value. And when the loop ends, current dot left becomes null, and this means that current is pointing to the leftmost node, which also contains the minimum value in the binary search tree. So we simply return current dot data. Okay. Let's go and run the code now. As you can see, we got the same output as the previous two approaches. So for the dry run, for example, if the tree is 4 to 1, current moves from 4 to 2 and then to 1. Since 1 has no left child, the loop stops and then we return 1. So here we traverse only the height of the tree. So the time complexity is big O of h. And since we are not using recursion or extra space, the space complexity is big O of 1. And that's why this makes the iterative approach the most optimal solution for finding the minimum element in a binary search tree. Thanks for watching.